Okay, good morning, everyone. Welcome to the ELIXIR Friday Coffee, where we are presenting the tools and services which were developed by the ELIXIR Czech Republic. Today, Martin Modrák will introduce the simulation-based calibration, which is an R package for validation of statistical models and algorithms, which I hope he will find a great solution for your problems. So, Martin, the floor is yours.
Hello, everybody. Let's dive into it. What does it mean? Why you should do it? Or maybe you should not do it. I don't know. Like we'll see. We'll see. Hopefully, you will find that useful. This has been work where it's a very international team of people I met over the internet. So thanks Yunji, Shinyung, and Temu for working on this with me. And I'll first try to explain like why would you want to, even do this thing and what motivated us to develop this kind of package. And so like the first obvious question is like, why check your models and computation at all? And like a lot of people don't. There are a lot of people that just don't check their models and computation, and just to be clear, I'm speaking about statistical models here, where like a lot of the tools we use are a statistical model in some sense. But not everything we do is a statistical model. So for the people like, none of this applies if you're not doing any form of statistics. On the other hand, quite frequently, a lot of the tools we use is doing some form of statistical argument or an approximation to a statistical argument. And like in a lot of cases, people don't actually check their models or computation. So in a lot of published papers and tools, you see like people derive that, for example, in the limit of infinite data, they can approximate their results as a normal distribution, and then like from then they like proceed, okay, everything is okay, we'll make the normal approximation, and we hope that like we're sufficiently close to infinite data for this to hold, and then like don't care about anything else. And like I think that's not good practice, but people do it. And it's definitely easier to publish if you don't check your models. So like you also may want to consider that like the more you check your models, the more likely you are to find a problem, and the less likely you are then like to publish. So that's also a thing. Like so, but we'll start with the premise that that we want to be correct. That's an important thing. And in this sense, like checking your models and associated computation is super important because like we all make mistakes. There might be mistakes in our mathematical reasoning, there might be mistakes in our implementation, and we need for a way to check that like if they're not, that there are not so many mistakes, or that at least they're not very important. So that's like one part of the motivation. Anyone is may have noticed that this package is primarily focused on in the Bayesian context, in the Bayesian interpretation of probability. And there's been like lots of discussion since like around like early 20th century between the frequentist and Bayesian schools of statistics. And I don't want to go into those controversies today, because in the end, like the most important distinction is between careful analysis and reckless analysis. And careful frequentist analysis often derives the same conclusions that a careful Bayesian analysis would do, and reckless analysis of all sorts of statistical solve can be problematic. So but I personally like the Bayesian approach to statistical inference, and one of the reasons I prefer it and why it makes stuff simple is that this like usual Bayesian argument that you have a belief about something, you collect data, then you get some posterior belief, comes with very useful tools. So regardless your philosophical stance on whether probability should quantify belief, or whether it is allowed to assign probability distributions to parameters or not, which is like part of the disagreement between the frequentist and Bayesian schools. So regardless of the philosophical commitments, what I like about the Bayesian approach is that it lends itself to some workflow and tool approaches that are also possible with frequent test approach, but are much less natural. So SBC, the package I'm going to talk about, is one of those ways that like Bayesian models lend themselves very naturally to tools and methodologies that let you be safe when developing models, and that lets you catch mistakes you make when developing models. So that's the primary focus. And as we'll also talk about, like in quite a lot of cases, the difference between a frequentist computation and Bayesian computation is not that big. So there's a lot of connections. So even if you don't buy the Bayesian approach, I hope you'll find the ideas presented useful. And one of the finally, like one thing I want to mention that's in the same way is that like there's a common argument that everything is Bayesian. Like you will say, okay, like all sorts of models that work because they are an approximation to a Bayesian procedure. So you can say lasso or wish regression or various forms of regularization, deep learning, and dropping out neurons in deep learning. All of those things can be understood as an approximation to some Bayesian procedure. So that's like a frequent argument. And once again, I'm not sure you have to buy it. I just want to show there are connections between a lot of the frequentist arguments and a lot of the Bayesian approaches. And that's why I don't think the distinction is actually that super important if we are being careful analysts. And so this is from a recent paper I helped with, and this is like an idea how a model development workflow can look like. And you may notice there's a lot of steps. I don't expect you to read all of them, but this figure was resulted from an outline of like what can we do when we develop a model to make sure that the model is correct. And you'll notice that simulation-based calibration, which we are going to talk about today, and also like which is tightly connected to fake data simulation, is just like one of many steps that you may want to do when developing a model. And quite frequently, like people don't do this, but once again, as I said, if we want to make sure that our models work, there's a lot of stuff we can do. In any case, what we can do is that we can validate our computation, and that's what we're going to be focusing on today. And there's also other stuff that we can do, like check that our model is compatible with the data we want to use, and that's a completely different question from like whether our computation is correct. So, like to very briefly summarize the big figure I've shown previously, is that there are like two broad types of common problems with the statistical model for any task you're doing, from differential expression to phylogenetics, to chip-seq analysis, to analyzing RT-PCR data. There's a lot of, so there are two types of problems. So one of them is there's a bug. The code doesn't do what we think it does, and there could be a mismatch between the model and the data we want to analyze. And as I said, like we're gonna focus on the first thing here, like how to prevent from bugs in our models. And data model mismatch is a different problem that has different tools that I'm not going to talk about today. Yeah. Okay. So what we're going to do is that we're gonna use simulation to the rescue, right? And so how do we separate bugs from a mismatch between model and data? I can just use our models on some real data set. We get some results, and then like how do we know why do we get these results? And the main idea is that if we simulate data exactly as the model assumes, then any problem has to be a bug. So we're not going to use any real data. We're going to simulate the data, and in this setting, any problem has to be a bug in your model. So that lets us isolate bugs in the model from the rest of the problems. And here, once again, connection between frequentist and Bayesian approaches is that the prior distribution that frequentists don't like, they feel like, you have subjective prior, they're useful because they define our simulations. When you want to do a simulation study with a frequentist model, you need to do something like a prior. You need to decide, okay, so how I'm going to simulate the data, and you need to bring some knowledge about what are plausible values of like log-fold change in differential expression. And in a Bayesian context, your model already does that. So you already have this ready, so that's nice and useful. And if you're a frequentist, you need to do it anyway if you want to do simulation studies. We need to define like what are plausible values of the parameters which we want to test, build our simulation studies with. And so this is an example like how simulating data exactly as the model assumes might look like. And you may notice this is a simple code to implement a regression model and a STAN, which is a probabilistic programming language that's not super important right now, and R. And you'll notice that there's like a very strict correspondence. We have a normal distribution here. We have a normal distribution here. We compute mu in the same way. So this is what I think when I simulate data exactly as the model assumes, is there's a really one-to-one correspondence between the model as we implement it and the model as we simulate it. And in some languages like STAN, this can be made very, very explicit. And so like what do we do with this? So like let's say like we run the model, we get some estimates. So this is like the mean estimate, and there's like some uncertainty interval here. And so like how do we spot a failure? So if the true value of this alpha variable is 0.3, so that's probably okay, I guess. Like it's well within the uncertainty interval. That's probably okay. So like, what if it's like 0.007, and then like it's kind of like outside the uncertainty interval, but a little bit. Is that okay? And like the idea here is that like a single simulation rarely tells us something useful, because like it could happen that alpha is very low even though our model is correct. And on the other hand, if it's like 0.3, if we had like too many simulations where just the model hits exactly the parameter, that's also suspicious, because this means that this uncertainty bound is too wide. Yeah, so like it tells us that the uncertainty quantification is not working as we would like it, because all the time we hit straight in the middle. So this is probably too wide. The rare exception is when we have like when it's ridiculously out of line. So that's like one of these situations. And then like we can really say like this is just from a single simulation. But we usually just need to run a lot of simulations to understand what's happening. And finally, like, how do we spot a success? Like, what does it mean for a model to work? Like, how do we, when we say like we have some failures but they are not frequent, when do we say that that this is a success? And this moves us to the basics of SBC, or simulation-based calibration. And the main idea of simulation-based calibration is there's a simple consistency requirement we have. So it's something like that in 95% of simulations, the true parameter, as we simulated it, is within the 95% posterior credible interval, or uncertainty interval, or like confidence interval if you're a frequentist. And this is something that should hold also for frequentist models. And in fact, in frequentist models, this is like a more strict requirement, because in frequentist models, this should hold for all confidence interval regardless of how we simulated data. In Bayesian models, it should hold only averaged over the prior distribution. So actually, for frequentist models, we have somewhat stricter requirements, and it turns out they're usually not met because of various approximations. But like in theory, this should hold for both Bayesian and frequentist models. And for Bayesian models, it's a slightly weaker statement. And we can generalize that like for every x in x% of simulations, we get X% of values that fall within the credible interval. So like 50% interval should contain 50% of the true values. And yeah, this is a simulation-based calibration criterion that this holds for all X. And there are some technical details about how this should work that like are important to get right. And the main idea is that we for every simulation we sim the posterior. We need to get some independent samples from the posterior or approximate posterior, and we take the rank of the true value within the samples. So we can count the number of samples that are smaller than the true value. And across simulation, this rank needs to be uniformly distributed. And this turns out to be equivalent to the statement that for all, this is like all the confidence intervals contain exactly the right number of true values is exactly when this is uniformly distributed. There's like a simple argument to be made. This was first published by Peltz et al. And this is like, and important to make this work computationally is that there are other ways you could conceptualize this and they don't work. And here, what Peltz and al did was they spoke about validation of algorithms. So this consistency criterion holds in the case where the way we simulate the data, our statistical model and our algorithm are in agreement in some sense. They match. So all of them are nice complements for each other. And the original idea was to use this to validate algorithms. But the same reasoning can be applied to validating models. So if we believe we have a good algorithm, and if we believe we have a good simulator, then any discrepancy we see is a problem with the model. Yeah. And similarly, and so one of the contributions of the package is to move the focus from algorithms to models, because much more people develop models than people who develop algorithms. And similarly, we want to be able to move from like running a single simulation to see that the results we get are not ridiculous to 1,000 simulations where we see that the model is very robust and moves like smoothly between those two extremes. So that's also like a workflow thing we try to make with the SBC package. And how do we move from a simple model to a complex model? So like usually we cannot just like implement any model, just like write 1,000 lines of codes and just run it and it works. That never happens. We always have to, build small things, test them separately, put them together. So these are some workflow considerations that we try to focus on with the package. And I can't really go into details of how that's done, but there are examples on the webpage of the package that kind of go through how you can use this to build your model in small steps and be safe at each step. And once you do this, here's like an output you might get. So these are the ranks that I talked about before, the number of samples that are smaller than the true value. And this is how the output might look like. So we'll start with like a uniform distribution of ranks, and this is what we should have. This means our model is well calibrated, everything works well, and you'll notice there is some noise here. Yeah, so there is some noise, but it's mostly pretty close to uniform. This is like some expectation of the uncertainty we have. And we see that like it's mostly within this is a perfectly well plot. And we can diagnose actually what's going wrong when this does not hold. So in this case, we have a lot of in the second case here, we have a lot of extreme ranks. We have a lot of ranks that are almost zero. We have a lot of ranks that are almost the maximum number, which means that our model is too certain. The true values often lie completely outside the uncertainty intervals provided by the model. Similarly, we can speak about the model being too certain here. Yeah? So we have a hill in the middle. It's an overabundance of ranks in the middle. So it means that the model is having wider confidence or credible intervals than we would want. We can have the model underestimate or overestimate these. Yeah, 5 minutes. We'll get there. There are a lot of stuff and figures that are optional. So yeah, 5 minutes is going to be okay. The model can be underestimating or overestimating, and we see all of those in those rank diagrams. So here we have an overabundance of small ranks. So like most frequently the true value is smaller than what the model tells us, and we can see exactly what's the problem here. Yeah, and this is just another visualization of the same thing. That's a bit more rigorous. That's a work by Teemu on making this a bit more rigorous, because here the uncertainty intervals are approximate. Here the uncertainty intervals are exact. So we want the black line, this is the observed cumulative distribution function of the ranks, to be within this blue ellipse. And once again, here, this is perfectly okay. The black line is within the uncertainty interval. As the model gets too certain or too uncertain, you'll notice those S shapes here that go outside of the interval. And there's some theoretical appeal to those visualizations. And particularly that they are like more reliable. And you'll notice that those two waste a lot of space. So one thing we can do is we can look at the same data just rotated 90 degrees, and this just shows up like the differences are now very clearly visible. That here there's something that's a problem. Here's a problem with our model. Similarly, here's a problem, for example. And finally, we can look about what we care about, and usually that's the coverage. So we usually, those plots are theoretically super appealing, and those plots tells us exactly what's happening. So here we have interval width and coverage. Once again, this should be uniform. So this should match the diagonal line. But once again, here we see that the model is too certain, and that means that, for example, here it says like that, like the 90% credible posterior interval actually covers only around 75% of the cases, and this is something we are interested in. So if we're going to interpret our inferences, we need to be able to check like what's the actual coverage, and if our confidence interval are too narrow, then we'll have like our 90 or 95% posterior intervals only cover 80% of data or something like that. So this is something we care about, but you may notice that it doesn't really, isn't able to check. For example, here it looks like there's no error because the model, the coverage is right, but the model is overestimating. So those plots are useful for interpretation, but they are not so useful for checking if your model is correct. Those plots are way better for checking like if something is wrong with your model. And so I will show just one practical example to avoid going over time. And there's going to be, and I'm going to go the second one, which is a phylogenetics. This is our work. Most of this work is primarily done by Luis Carvalho from Rio de Janeiro. And here the idea is we are estimating phylogenetic trees and associated parameters from mutation models. So you've probably seen some phylogenetic models. You get sequences from various species or variants of a protein or virus or something, and we want to understand the population history, how these sequences came about, which species are more closely related, and these kind of things. And this is quite frequently done with Bayesian estimation, and it's extremely challenging. The space of trees is extremely unforgiving. There's a lot of problematic cases, and it's for example, this work was done with the Beast software, which is a Bayesian estimator for those trees. One of multiple. There's some Mr. Bayes. There are other tools that use Bayesian approaches because we kind of know that we want to quantify the uncertainty. There's like it's super hard to speak about frequentist. Well, the frequentist approach is a bit less approachable, and so the Bayesian approach is where we need there. And one problem is, once again, it's super hard to claim like if your software works, because usually if you simulate the data, the software will not recover exactly the same tree as you simulated the data, but hopefully the tree is going to be somewhat similar or have important features exactly the same. And so we can, even for this very complex model, we can do SBC. We can simulate a lot of trees from the prior, and then expect how they behave on average across all of those simulations, how they behave, and see if the uncertainty that's reported in the trees or in the branch lengths and other parameters of interest is correct. Yeah, so we make our hypotheses over trees about some evolutionary history. We see how well they are supported. And so this is, for example, one of the results they got. And this just shows that there are two variants of the algorithm. And you'll notice that one of them, the uncertainty, is problematic because it has an overabundance of like somewhere slightly above center. There's an overabundance of simulation. So there's something problematic. But there's a proposal to do this differently that doesn't have this problem. And this works in the super complex models and situations where it's super hard to validate, and you get like some ground truth data. So that's all about the package. There's a GitHub link for you to use. There are examples and vignettes that explain how that's applied to simple models, primarily in Bayesian statistics. And yeah, and I'm happy to answer questions.
Martin, thank you very much. And if there are some questions. So first is, if your analysis can be applied, for example, on MD simulations or biomolecules, or the stuff where you have in the simulation of the 3D bioinformatics, for example.
Yeah, so this applies whenever you're quantifying uncertainty in some context. So whenever the output of your algorithm is an estimate with an uncertainty, this can apply. The limitation often is computation. So if you want to really be sure that your model works, then you need like 100 simulations or 1,000 simulations. And in the context where like a single fit, like simulating the data, fitting the data, takes a day, then running 1,000 simulations is not very practical. So you need to be a bit more clever about it. But yeah, but so I'm not familiar with these biomolecules approaches, but whenever what you're making is a statement about uncertainty, then these kind of approaches, averaging over multiple simulation and exploring the ranks, can be useful to understand if your model is well calibrated and your uncertainty estimates are well calibrated. So okay. I hope that answers this question. Okay.
So and on the GitHub, so there are prerequisites to install the package on your own computer.
Yeah, so like it's a pretty standard R package, and it depends on a couple of other widely available R packages that are on the CRAN. So it should be quite straightforward to install. Most of the R examples are with the Stan programming language, because this is where this originated. And Stan can be a bit difficult, can sometimes be a bit hard to install, especially on non-Linux machines. But like the package doesn't rely on Stan, it's just most of our examples use it.
Okay, and when people get lost, so they can contact you, right?
Yeah, sure. Yeah, we have a nice community around the Stan language, so there's a forum that's pretty active and also accepts questions about these methodology and workflow things around statistics.
Okay, Martin, thank you. There are no other questions, so thank you very much, and see you next Friday, 9:30 on the ELIXIR Friday Coffee. Good day. Bye-bye.
Okay, yeah. Bye.